Good evening, everyone. It's working. Thanks very much for coming. We have this evening Colin Gravill here from Microsoft Research, who's going to be talking about biological computation with F#. As you may have noticed, we're not in our usual venue. You've probably heard the news about Skills Matter, which was pretty sad. So they've been incredibly supportive of us and the wider technology community in London for a long time. So please do think of them and their employees if you have any or are aware of any roles in kind of event management, community organizer type areas. Please do get in touch with them or think of them. And thank you very much to G Research for stepping up with a venue for us for this talk. It appears extremely high quality from what I've seen so far. We're going to be putting their AV equipment to the first external test, I understand, so see how that goes. But thank you so much for providing us a venue and also sponsoring drinks and pizza for after the meetup. As a result of the Skills Matter situation, there's no regular venue. There's also no F# Exchange conference going to happen next year. There are some people talking about scheduling something, but it's pretty early days at the moment. I've had several offers of venues for further F# meetups, and I'd be very happy to keep organising them. What I do need are speakers. So if you've got anything you'd like to talk about, or you know someone who does, or if you'd like to do something in a slightly different format, for example, a workshop or a lightning talk perhaps, please get in touch with me. I'm Mark Patterson. You can find me on Twitter or via the meetup group. And hopefully we'll get a good schedule of meetups in the calendar for next year. I think that's all I need to say. So thank you very much. And David, you comment.
Okay, can everybody hear me at the back okay? Yeah. Okay, great. So my name's Colin. I'm based at Microsoft Research in Cambridge. What we're trying to do is treat some of the things that biology does as a bit more of a programming or computer science problem. Can we use some of the same techniques to get a bit more of a grasp on how biology makes decisions, but how we might be able to kind of repurpose it to make more efficient medicines, more effective ones as well. So what I'm going to start off by doing is just talking about what I guess most of you folks do. You program silicon in the form of chips. Now if you approach this problem like a biologist would do, is your first thing you would do is you get out an electron microscope, or you trying to kind of examine what's going on structurally on it. Now there's a lot of like city block-like structures here, so it's quite regular because of the nature of it. Now, again, what you would do as a biologist is you might try and take out one part of it, or disable it, or just apply some currents at random paths across it and see what's happened. Now, obviously, that sounds like a ludicrous way to try and program a silicon chip. That's partly because we've built it for our own intentions, and we have abstractions to work with. Now, so another way you might approach this, if you were learning, you wouldn't necessarily start with a chip like that, is you start at the other end of the scale, like take the fundamental parts from electronics and kind of try to wire them together and then build up from the ground. And there's this really great book on kind of elements of computer programming, and they ask for some things from the outside to start off, to go all the way up to Tetris from NAND gates. And so a couple of things they need are flip-flops and NAND gates. And somebody kind of asked the question, how do you actually make one of those? And there's this wonderful forum post where they're talking through wiring this up. So how do you go from fundamental kind of electronic components to something a little bit higher up? And then there's another person who posts as well, where they provide a kind of schematic. And this is going to be important as I kind of talk through what we're doing on the biology side. You've got both the physical system that has certain capabilities and properties, but you also want to be able to think of it at higher levels, or kind of work with it in slightly more abstract ways. Because wiring up individual components is not how we achieve amazing things with silicon chips. And it's not how we think you'll be able to achieve amazing things with biology either. So these are just kind of books the one I was talking about. I really recommend it if you want a more fundamental understanding of the steps of programming, how you go from logic gates all the way up. But anyway, I'm here to talk to you about biology, so something a little bit different. I'm going to guess there's probably no biologists in the room. If there are, the prior apologies for any license I take or explanations. You can interject and correct me, I don't mind. And similarly, if anybody has questions going along, that's also very welcome. Okay, so we have some biology. We want to put it to a purpose. And again, we get our microscope out. Now, slight confession, I don't actually know if this is a simulation or actual cells moving. But it's kind of similar to one of the systems we work with. And it's showing like this kind of evolution of individual units and achieving larger scale behavior. And it's not very impressive in of itself, but again, if you start thinking from like a blinking light on an electronic circuit board, and then we build up abstractions on top of that. Okay? And again, this is a schematic version of one tiny part of a cell in the metabolism system. Not very useful. It's mainly shown to people to like reinforce biologists exposure to like massive amounts of complexity. Again, this is probably not directly how you want to interact with the system, but it is useful to have a kind of atlas of how one part of the system you might be working on. No intention to try and teach this to you. Okay, so what do we do in the group I work with? We have these kind of 4 main areas that we do more and less on over the years. Immunology is kind of how your body keeps itself safe. Developmental biology is how we grow from a single cell organism and how tissues make choices. Synthetic biology, some of you might have heard of. There's a bit of an ongoing field of like engineering in biology. And also molecular programming is a little bit more speculative out there research that we do. Of can we take DNA and hack it up into pieces and use that as a kind of more compute-like substrate? So one of the ways we manifest this is by building tools. I'm a software engineer, and so this is one of the many ways I contribute. We also produce papers and contribute to basic research. In the interest of time, I'm just going to talk today about 2 areas. I think they kind of cover 2 interesting aspects. One of building things up from fundamental parts, and the other of can we make sense of existing systems and in biology and things they do, again, using computer science and software engineering-like tools. Okay, so I'm going to start with one, the molecular programming side. And what we're doing is we're programming with DNA, and you can start thinking of this as machine code if you want. So it's the manifestation of the system. So this is what's in all your cells. It's got the code for building up the functionality that humans and all of that creatures have. But again, you want to have these different views at the same time. We can label these things as letters, but there's also kind of a molecular basis for that. And it's important because what I'm going to talk about is how we might repurpose that. So we have these pieces, and like the strands you saw earlier, then this is again a representation. It's unraveled, so they're flat, so helix is all twisted up. But these are the molecular parts there. And this is fully connected, so there's every part has a pair. And so what we're going to do is make use of this. Now the only rule I really need for this work, what I'm going to talk about here, is that these short bonds, they are quite weak. So if I go to test tube and put a whole bunch of these ones at the top, and a whole bunch of these ones at the bottom, they would bounce into one another, and stochastically, some of them would join, some of them would break apart. These ones down here, because they're longer, the overall bond strength between the connection then becomes latched in place. So these bonds will not break apart naturally. The other part is that the length of the bond is held together with much stronger ionic bonds. So this again requires more technology to take it apart. So most of you have probably heard of things like CRISPR and other techniques for editing DNA in larger scales. This is going to be quite different. So what we're going to put this for a new and different purpose. However, and just so that people catch the change, it's a bit annoying. Like in computing, you don't list out exactly the memory locations and exactly what's happening. You have identifiers and labels for things, because then it becomes easier to work with. So what I'm going to do is just go through here and label them. So I'm just doing it with numbers. The 1 star is just the reverse, because sometimes you want to refer to the mirror image molecularly of the other one. So I'm just going through here. Now they're joined together, they're still the same strand, or we call these toe holds for like a location that can easily bind and unbind. And again, labeling is down here. So in this system, we have 2 different types of strands. We need to produce it from somewhere. There's many means of doing that with enzymes or other technology. I just want to give you the kind of like a feel for the molecular structure of what's going on when when we don't get a video. Okay, my first video work, this one is not in a working state, I'm just going to skip along. What this shows is an element floating in and pushing off the other section. Like it does a kind of random walk to move the other section out. So earlier, when I said this section can't unravel naturally, if there's another section that can it can grab on the toehold section, it can push off the other longer leg. I've got some other descriptions of that in a second. So this is just a kind of pictorial version of that. So if you imagine like an equation, you put this bit of DNA as well as this bit of DNA here. What it's showing is this 1 will bind on, which it can hop on and hop off again. And then this 2 is pushing off the other 2. It's walking up and down with the molecular bonds. But it's always important to bear in mind as well, there's a full complex structure going into this as well. Now, this is the more schematic view of one of the videos I want to show. And what this is showing is the kind of equivalent to an AND gate. So you have these small pieces that you might put into solution, and they bind on to the larger molecule, and then they walk up and push the other section out in the middle. So just going to check in, does it make sense for people? You need both of them to be able to push off the section in the middle. And so what we've done with molecules is kind of created an analog to an AND gate. Now, again, we kind of come from a languages background in computer science. So spelling these things out with reactions, like writing them out one by one, can also be less efficient. And so we've built up a language called DST. And what this is showing is, I'm just going to set this through for people. So this is just a bit of infrastructure to show how we're going to plot afterwards to see what's going on. But the bit to look at is this section down here. So input 1, and again, if you think back to earlier when I was saying, rather than spelling out long DNA sections bit by bit, which would be tiresome, instead we can just use a compiler to do that for us. So this 1 is a bit of DNA on a top strand. The hat is saying it's a short section, so we need to communicate to the compiler. It's a long section that binds irreversibly, or a short section that will bind on and off again. This is a second input. And then the backbone, which is in a sense the AND gate, is this part down here. So again, the syntax of this, we've labeled it. We have said in this case it is a short strand, and this star is saying it's the mirror image down at the bottom. And then what we're doing up here is we're saying how many of these molecules are we going to chuck into the solution. And this is going to affect, if you imagine rather than computing where you're controlling the input to the system, you're instead putting them in a big soup, and maybe you're stirring them up a bit if you want to make them react faster. But in general, the more of them are, the faster they're going to react. So, okay, what I'm really trying to do here is show you the really basics, the very getting started with molecular programming. And so one of the tools we built is called DST, and you can search for it. It's freely available. There's some source available for academic use. But what we can do is we can take that example I was showing earlier. Is that legible? People at the back? Yeah. Okay. And then we can say, what's going to happen in this kind of complex molecular setup? And what we say here is, instead of simulating in a mathematically pure sense of perfect deterministic rates, we're saying there's a bit of randomness in here, and also because there's relatively few molecules, so there's relatively low numbers here, you're going to get these stochastic effects. So if we run a simulation, we'll actually get ever so slightly different numbers over and over. Now, if I were to turn up the number of gates, so there's more things, then you see how you get these smoother curves, and this is kind of, yes?
Sorry, the expression at the end, what's the output of that? What's like the type? What does it mean? What does it represent? Can you compute that expression at the end? The last 4 lines?
Yeah, okay. So I'll break this up into pieces. This is defining what's in the system, like the types of things that you can put in. This is defining the number of them, and this is an instantiation of it. So this is saying, take these numerical constants and initialize that many of those gate types. Does that make sense? Yeah. Okay, so I'm going to use a test now. We've built an AND gate here. So there's lots of gates that we use in electronics. Does anybody want to take a guess how we might be able to build an OR gate?
So what's the biological purpose of building this simulation? What are you trying to model biologically, or?
I'll get to examples where you might use it. So this doesn't exist in biology. We've taken DNA and we've taken it apart. We're then taking that DNA and using that to do computing. So there are a lot of situations in biology, if we can insert a small amount of computing, we would be able to achieve useful things. And I'll talk a little bit more later about that. Yeah?
So is there 40 molecules of the output molecule 2, 3, is that right?
This is 40 of the AND gate, so the substrate that things are binding onto.
But the output molecule is bound to the AND gate, is that right?
No, it's actually pushing it off. If I jump. Oh, yes, sorry, you're correct.
So why is there more in the system at the end than 40?
So there's a scaling rate up here.
Okay. What does that do?
It scales up the numbers. So I could try going a little off piece here, but if we scale it back down, I have to check the numbers whether 25 times 5 adds up to the right number of things going into it. But you're also then seeing a lot more stochastic effects here of jumps. So I was mainly just shifting the numbers for just to be able to show the differences. Using the scale would have been another way to do that. Okay, anybody jumping with any ideas how we might build an OR gate? So if we look back to this kind of schematic diagram, we've got this section here that's being pushed off by these 2 bits at the outside. Okay.
I guess if you had the bottom one would need to be 3 on, then you might have to say 1, 2, 2, 3 on top, and either of them would push it on.
Yeah, I think if I'm understanding you right. So just before I go ahead, what I'm going to do is just demonstrate that this is in a sense working. If I stop giving any inputs on the AND gate, we're getting a lot of these inputs, but we're not getting any outputs. And if we flip it over the other way, similarly, we are also getting some of the other inputs, but we're not getting no counts on the output. So now I'm going to try it what I did, and we can test if it behaves like an OR gate. Okay. I've done this before, but I have it messing it up. Is that what you have in mind?
Yes.
I'll give it to you anyway. Okay. Let's see if I've made any mistakes. I'm just going to increase the scale of this. I will explain in a moment why I'm shifting these. So in the case where you had an AND gate, you actually needed both of them to come kind of similar times, and because they can bounce off, that's actually quite unlikely to occur. In the case where you only need one or the other, it's a much likelier event to happen. So the chance of arranging, in a sense, 3 things in time in a big molecular soup is a lot harder than arranging 2 things. So that's why I'm just messing with these numbers a little bit. So the numbers we're running with here as well, these aren't calibrated. I'll talk a little bit more about how we calibrate them for real systems. But yes, let's see if we can get this to work. So last time when I took out one of the inputs, we no longer got, yeah. I also need to shift the plotting up here as well. Okay, so we're still getting outputs, and so earlier, when we took out one of the inputs, we no longer got any of the outputs in the AND gate. So if we try that experiment this time, we still get outputs. So we've got these structures. This is a way that we can experiment with what might happen in the wet lab. But this is again like very fundamentals of computing. So we've done some more experiments, but we've taken this further. We've built up like square root circuits, 4-bit ones. But there are also other cases where we might want to for example, deliver a medicine. So this is a different lab, not one we worked on this project with. If you take the DNA and do something again a little bit different, and you kind of do like a bit like basket weaving, you can take a molecule and slot it inside. If you then put on the outside a kind of molecular logic, so that it needs to be able to see something else to unlock. So if the structure holds it together, like as almost literally like a loop as a lock, and you have primed it so that in the exposure to something in a body. So one of the suggested approaches to this is like if you detect enough cancer markers, you could then unlock the box, which means you can do kind of selective delivery of chemotherapy drugs. This is a lot of quite speculative research. This hasn't been done in people or animals, but it's demonstrated kind of a lab situation. So we've been generally working on showing how this can be used as a kind of universal compute structure. And indeed, for people inclined that way, it is Turing complete. There's some awkwardnesses about expressing NOT gates, in that if you're working with molecules, it's harder to express the lack of a molecule. So there's again an approach, a dual well logic, which allows you to express the absence of something. I'm not going to go into those details, but this is one way that people have talked about. We could import kind of digital logic, control theory, and we could stick this into a biological situation. So one of the big things we work with is people who use big, large-scale bioreactors. So they grow medicines through genetic alterations. And one of the challenges there is putting a little bit of logic. So if you could arrange for the cells to coordinate more, they will be able to grow up and then start producing the medicine. Whereas what you've actually ended up with is a bit of a hodgepodge of different things. Okay, so I talked there a little bit about a system, and I've shown a simulator. We can also repeat those experiments in a kind of wet lab context and show that things behave like this. Again, examining things, putting fluorescent markers. But if I'm going to start talking about like potentially you could use this in a treatment situation, you need to be able to say like this is correct, like this actually does something that you intend it to do. So we want to say a little bit about how do we establish that these simulators are doing what we intend them to do. And for anybody who's familiar with FS-Check, then I will start with the terribly cliched example. So a lot of people, I'm guessing most of you are used to doing unit testing of some sort. You have an example about how your system should work. You run your system and you measure the outputs. That can be difficult if your system is very complex, if it has a lot of different entry points, and particularly if you have like compilers. Now you can try and do like selective testing, you can try and do fuzz testing. This approach I quite like, of like describing the properties of your system. So to take this example, if you're dealing with lists, if you reverse a list twice, you should get back to the original list. And so one way of testing the behavior of your list reversal is by expressing this property that it's idempotent over double reversals. You then test that by generating a large number of lists and then comparing the two sides of them. So this has been used in a lot of areas, and it's, I I think of this as kind of generative testing. If you describe to your system how to generate the tests, it can then generate a very large number of those. Okay. So the syntax for doing that is, with fscheck, is I'm going to talk here about generating lists of integers. You can generate these individual ones, but you can also compose them together. You can say, I want to generate tuples of lists instead. And so you can then test the behavior over these properties in your system at a slightly higher level. Okay, so now jumping back, so why do I actually want this technology? What purposes am I putting it to? So earlier on, I was labeling different parts of the system with numbers. In this case, we're starting to label them with letters. Again, doesn't really matter. Identifiers in a programming language as you want. What we want to do in this case is test that our rules about how these molecules interact obey certain constraints. So in this case, the same number of molecules on the left and the right. So when you're writing a system with a lot of these complex interactions, it would be easy to make a mistake. And what we could do is try and exhaustively test it by trying many different examples. But given that we're building a compiler for other people, there's this other approach of if we take the bound together molecules and we melt them apart, and if we were to do that on both sides of one of the reactions I was talking about earlier, we should have the same things on the left and the right. So the property is that there's a conservation of molecules under this as an assumption of our system. So we've got a reaction down here, and we melt it apart, and probably by eye you can look at this and see that this element here, this element here, this one here, and this one here, they all match up. They've got bends in them. In the case of like floppy molecules, that's not important. So how do we do this? So we have the textual representation. I showed you a bit of this earlier, but it's starting to get a bit more complex. So there are these binds on here to represent these overlapping molecules. But what that is just showing is like the join point between the two sides. So you start to see down at the bottom why we need a more complex, perhaps more generative approach for testing. So when we're gluing together all these different molecules, it'd be quite easy to write rules that interact with them incorrectly, especially when we're starting to get these kind of complex structures at the end, which can be used to hold on to other parts of molecules. And so, just to kind of highlight, this is one of the reasons why we like F# for this type of programming, that we have a very rich domain that we want to reason over. So what we're able to do is kind of encode these, the double is the double bond section, the hairpin is that kind of loop just at the end, and we're able to quite directly map into the structures that make it up. Now, I'm not going to expect any of you to like follow the exact reasons why we've structured F# this way. I just wanted to highlight it's a relatively compact form for something, again, relatively complex. But the relevant thing here is that we're able to do the same thing I did earlier with generating lists, to use it to generate these different sections of the molecular elements that we want to reason over. And again, we can build up these sections. There's kind of a very nice direct correspondence between domain-specific language that we use for parsing and generating it, but also the generators for running testing of it. And we end up writing like relatively little code, but we've been able to detect very subtle bugs in our calculus or the rules of the system, how we put it together. So we've also been able to use this on other systems that people have built in kind of molecular programming that have bugs in, but only show up on our simulators. They don't really show up, obviously, in the wet lab until you push it to more extremes. Yeah, and just mentioning fparsec, which is the tool we use to do the parsing of those textual structures. So we have a couple of different routes. We can either use fscheck to generate the data structures directly, or we've also used fscheck to generate strings, which correspond to the rules for the parsing as well. So we're able to use fscheck to check up rules are our own system, but the rules we use for parsing. And then we're also then able to establish that we have kind of symmetry between, we can take one molecule in the system and send it into a string, but we can also turn that back into a molecule as well, which is helpful for us. And it's meant we can get, we're no testers, but a relatively a convenient way to get confidence our systems in the simulator doing what we intend them to do. Okay, so let's talk about a little bit about how we use programming techniques to measure the correctness of the simulators as we intended them. But we also want to understand, like, are we correctly describing the systems we work with? So this is going at a slightly more biological level. So I talked about the logic gates, and a lot of people, when they hear that, they immediately kind of ask me the question, are we going to then just replace all computers? Sorry. Are we going to then immediately replace all computers with biological computers? So shall we stop working with silicon? Shall we instead build logic gates? And the reality is that they're quite slow. They take hours for some of these reactions to happen. You can speed them up by putting them onto a substrate, but it's still quite slow. The interesting thing is that there's kind of a bit of an overlap between putting a little bit of intelligence into different situations, so like in a big bioreactor or into somebody. But you also can, rather than kind of recreate like centralized logic, then the biology itself is making distributed decisions. So rather than some situation where you might go through and count, like, do you have more of one species or more of another species, you can actually encode those logics directly into the interactions themselves. I'm going to talk through a paper that was published by our group a few years ago. And this is an algorithm that's also talked about in systems theory. So imagine you're in a situation where you've got trillions of something and 2 trillion of something else. It would actually be hard to run around and locate those things and count which ones. So if you had to go out into the world and count those individually. Instead, what you could do is arrange for an algorithm. You can actually run this, I've never done it, but you can arrange this as a kind of party game. If people come with a preconceived notion of, like, I believe in X or I believe in Y. If you meet somebody else and that person has your same preference, you can just stay the same. If you meet somebody with a different preference, you flip to this kind of intermediate state of I'm not sure. So if you think about it, like, I strongly believe in X, but if I meet somebody who believes in Y, I'm not so sure anymore. But if you're in this intermediate state of, like, I'm not too sure anymore, if you meet somebody who believes in X, you go back to X. Or if you meet somebody who believes in Y, you flip over to that. Now, it's not immediately obvious why this actually works. You have to kind of think through the kind of stats of the likelihood of bumping into somebody who believes in X. If there are more people in the soup or in the room who believe in X, then you're more likely to run into them. So it creates a kind of bias. And there's a kind of a short video to highlight this. And so what this is showing is a kind of progression. And I just highlight again, like, all the things I'm showing, these are all things that we've run in our own wet lab and validated that they happen in practice. The rates that they happen are then somewhat interesting. Now, what we're going to do is like think through how do we build these set of interactions. So I showed before things like AND gates, but instead of going with that kind of approach, where we're trying to build these other structures. And so this, with the same molecules as before, we've got these strong sections in between and weak ones on the outside. And this will just kind of flow backwards and forwards. So it's a useful kind of molecular component that you can work with. And the one before, you were just getting a top section out, but if it's more easy to arrange your programs, and it's odd how quickly you go from like This is really difficult, like it's amazing we work with molecules or something, so I don't want to deal with that. My molecule isn't quite that shape. Can we just make like a longer chain of interactions so it's easier to reason and work with? In the same way, maybe you don't like the most performant computing because it's hard to reason about or communicate. So it's still implementing a kind of equivalent thing of its reversible back and forwards. And in this case, we've also got this backwards and forwards, but we're inserting a kind of equivalent to an AND gate as well. And for the system we're trying to build here, we also want to make permanent or irreversible reactions. Okay, so you can then take those components. I won't talk through the detail of it, but you can put those together to reproduce these. We can then run simulations over those set of interactions. We can make them in the lab. And what we're showing here is, if you look at this, the dotted lines are model predictions. These solid lines are best fit lines of experimental data we've measured in the lab. The numbers just above the charts are the concentrations of one, so the number of molecules that are assigned to the X state, and the number of molecules that are assigned to the Y state. And as they progress, you can kind of see them reaching a consensus in each of these cases. We also have other tools that kind of do probabilistic modeling, and when you look at these cases where they're much closer, you indeed get a small chance of a wrong answer. And it's a similar kind of situation you end up with distributed computing. If you trade off correctness, you might be able to obtain more performance. So if you need exact information about the finest detail, which is in the majority, you might have to take a different approach. But if you want performance, then being able to use these kind of distributed systems, and this is indeed like can be shown to be an optimal approach if you're willing to look for that trade-off. Okay, so I've spoken a little bit about our wet lab. I just wanted to make it a bit more concrete. This is our -70 centigrade freezer. I'm guessing I don't have to translate to Fahrenheit speaking here, so that's a little easier. We do that to stop parts degrading. If you've got something cold, you also need something to warm it up with. So for some of our systems, we can just stick it in the microwave. Other things, that's bad for it. A lot of what we do, some extremely competent colleagues of mine work in the wet lab, but it's quite onerous work. So where possible, we're trying to move to a model of being able to generate more data automatically with automation. So this is a robot liquid handling system. So we can prepare concentrations. So when I showed that the data are like sweeping across, it's kind of annoying for a person to have to like do each of those. And if you want more and more accurate data, at some point, the humans get tired of doing those experiments. But if we want to more narrowly constrain the world, we need a lot more data. And then to be able to see what you're doing, and this is the much talked about microscope, and that then runs, we can scan the parameters. It's got an automated XY stage on it, so we can gather data over different components, and then kind of analyze the results. Okay, so that is my kind of section talking about the molecular programming work we do. So quite speculative, using biology to implement computing, and there's kind of a natural pause there. I don't know if anybody had any questions about that, or I can just keep going straight on to the stem cell work. Yeah, sure.
You mentioned the microscope. There's much talk about. Why is there much talk about? Or did
I just this is how we look at things. It would be so nice to have like a printf statement in the middle of a biological program, but you don't have that easy ability. What you have to do instead is tag in halfway through your program a fluorescent protein, for example, and then run it for several hours and watch with a microscope to see when it goes high. So the hassle of, in a sense, logging of your system introduces some of these more like distractions in some ways. Oh yeah, there's another question there.
Can the tagging itself change your reaction?
Yes, it definitely can. The even more awkward thing is shining a microscope at it can change the experiment as well. So some collaborators actually found when they changed their fluorescent light bulbs, a whole bunch of their experiments changed. So This is one of the biggest challenges that is, I think, of as being at the root of reproducibility challenges in biology. You don't know the inputs you're putting into the system. You think you're doing these things, but actually a lot of other things are happening as well. Okay. Well, I think there's a question at the back there.
Yeah. So it's more about the simulation that you were showing about the substrate and the aggregates picking up, picking one another.
Yeah.
When one is sitting, the chiral, I don't know, the mirroring one that gets lifted for the other one to sit.
Yeah.
At some point, I suppose that there would be some competition between the two.
Yes. So there is a kind of, I think you're talking about when it's pushing it up and it's being disconnected. Yeah. So that's very much a stochastic random walk. You can set a bit of bias.
But you're always assuming that this is the process, so one aggregate will always kick the other one out.
Eventually, yeah.
Right.
And if you wait long enough, that does tend to happen. You do get some that are broken, and there are many reasons for that. So either when you're producing these things, your error rate is small, but it's still there. So you get broken gates, and it could be for many reasons.
Are those trans supposed to be RNAs that you're interfering with opposing RNA? Is that what those trans are?
They're not RNAs, really. So these really are like lumps of DNA that are there, they're convenient, and we work with it, but we're not treating biology as is. So none of these are things that will fold into proteins, for example. The next section I'm going to talk about, we're using we're interacting with biology much more as it is. Oh yeah, that's a question.
Are the kinetics of the binding regions, in terms of the short and the long, are they roughly the same depending on the different type of molecule? So between your 1, 2s, and 3s, do you find a bias? So you had this one where they would sit onto the same molecule backbone. Do you ever find like an equilibrium bias there?
You very much do get complex binding kinetics based on the lengths. So this is one of the reasons why we need to run a lot of experiments and then feed those into even larger machine learning models, so they get predictions about when people use different lengths. The actual bigger problem is accidental overlaps. So I've been cavalierly saying like 1, 2, 3, and 4, but you've only got these sections to write, these 4 letters to work with. If you accidentally have a short section that there's too much overlap with another one, you might accidentally bind there, block the side, and render it kind of inoperable. So that's something that you have to lean on the compiler to help you with, and then when it doesn't work, feed that back to improve in the future. Okay, I don't see any more hands, so I'll go on to the next section. So this is more biology as is. So this is approaching like, can we use computer science techniques to make sense of some things that biology does? And so one of the properties that we've looked into are stem cells, and in particular, the technical term for this is pluripotency. So this is an ability to become lots of other different cells, and stem cells can also self-renew. And what we want to do is to understand that on a more detailed genetic level. And a lot of scientists do work in this space, and a lot of things know, but we're taking a particular angle of attack. So just to emphasize, all your differentiated cells, so in your brain, in your heart, and in your lungs, they differentiated out from a stem cell. And they went through potentially many stages through the differentiation tree, but they did that in response to like chemical triggers. And we're going to talk a little bit about how we might better understand that. So there will be a diversion into more simple biology firstly. So the technique we use here is a satisfiability solver. So a lot of verification or understanding of systems is done using so-called satisfiability. So this is an approach like trying to find a way to reason about some logical states in the world. Like, can you find a solution that matches your constraints? So some of my other colleagues, not myself, in my group, they want to ask questions like this. So is there some way that running a protocol will accidentally release secrets? Or is there some way of asking will this program crash or halt or break? Now obviously, you're touching on really difficult problems there, like making statements about what programs will and won't do quickly leads to undecidability. The interesting thing is that SMT solvers are, one way of thinking about it is a quite effective brute force to intractable problems. And problems that were seen as like too complex to deal with, when approached in an effective way, have actually been resolved by approaches like this. So there's another project started in my lab called Everest, and this is attacking the kind of HTTP stack, building trustworthy security components, and they've also used the SMT solver. But again, I'm going to talk to you about biology, but there's a kind of direct equivalence between this idea of, is there a set of states you can push the system through that will also lead to an overflow? You could also think of an equivalent of, is there a set of things that we can do to these stem cells that will cause them to differentiate or make choices? And what are they? And can you tell me exactly what levels I need to put them at different points? Because if we can do that, then we can have influence over regeneration and also understand better development biology. But that's a bit complicated, so I'm going to start with a bit of a trivial problem. So, many of you will probably have heard of this example. I don't know why the farmer has these things, especially why a farmer has a wolf that he's taking out for a walk with his goat. But the rules of this game are, if you leave the goat alone with the cabbage, it eats it. And if you leave the wolf alone with the goat, it will eat that as well. The farmer can carry one item over with him at any one time, and he can go backwards and forwards. Now this isn't like a really hard problem. I mean, people will have solved this. You could sit and write this out. You could also sit and take a more conventional approach with a tree search algorithm, and that would also work out. But just for like a very simple example of what we might be able to do. So there's a very low-level API. So it's a C++ API, and people are used to dealing with. Everybody see? Okay.
No, please.
Good one? Yeah. Okay. Okay. Great. So what I'm going to do is encode the system in a quite direct way with these Boolean expressions. So we've got the near shore, and we've got on the boat, and we've got across the river. So each of the items I talked about, the farmer and the wolf and the goat and the cabbage, each of those things can be in a different place. We can also start to encode states and teach this solver about the things we don't want to happen. So we want to basically prevent eating. So again, this is a very low-level API that I'm working with. I'll talk about some options later. As wide as you can see. Basically, if the wolf is in the same location with the goat, with the farmer not there to supervise, it's going to eat it. And so these are bad. These are the equivalents in a computer program of an overflow, which we don't want to reach. So we're basically disallowing these states. Now you also have to spell out a lot of things in this abstraction that I've built up. The boat can only fit so many things at once. Also that there's no kind of weird quantum teleportation states. You have to be in one place here, definitely. You can't be in different places at the same time as well. And so we then combine it all together with no eating, but we're respecting the boat capacity, only one place at a time. And we then describe the transitions through the system. This is all getting a little bit painful about spelling it all out in detail. Why are we doing this? Can't we just write a tree search? There's reasons for this, which I'll explain a little bit. I'll just show that it works. And if anybody wants to try this at home, you'll be glad to know I've just converted to .NET Core 3, so it's I was not daring enough with demos that I was going to convert it on the day of. Instead, I converted it last night. So, And this will come up a little bit more later, this kind of visualization. So what it's showing is that there's a possible solution to this. So the farmer and the wolf and the goats and the cabbage are all on one side. The farmer goes across with the goat. So he's got onto the boat, then he's got to the other side. The farmer leaves the goat on the other side, comes back, takes the cabbage over. Oh no, the farmer's leaving the goat with the cabbage. Disaster's going to ensue, but he's ready for this. So he takes back the goat back over the river, and then can move the wolf over. The wolf is not a herbivore, so he's not going to eat the cabbage. And eventually everybody's happy. We've got to the far side of the river as the puzzle posed. In this case, this is a whole lot of effort we've gone to spell out a problem that, I don't know, it would be, any language, you could probably write out a very brute force tree search that would have got it done in faster than you can notice how long it takes. The nice thing about this is with an SNT solver is that you've outsourced to the heuristics of the solver a lot of information about your problem, and so it can very efficiently prune the tree. In order for that to start to become worthwhile, we need a harder problem. And this is where it started from. Oh, well, it's on GitHub if anybody actually wants to see how that's done. And just to mention in passing, somebody actually made a bit of a nicer DSL. They're talking about pet purchasing, like optimizing cost of purchases. But you can imagine at various stages building up a DSL to work with your problems. And so we've indeed done that in biology, but I just need to talk through a little bit about why the problem is hard. So we have, in humans, about this number of genes. The about is a bit of a funny statement, like determination of like what is a gene and overlaps. But they work by being transcribed into protein, as was mentioned earlier, like, into RNA and then folded up. Sometimes those transcription factors also then work to do other transcriptions. So it's kind of a self-aware machine with all the problems that produces in programming when you monkey patch, but this is a system gone wild. Just a short video showing that process of the initial transcription for the DNA. So it's working it through. Again, this is a much more dense thing in practice. It's sucking in these molecules, and this is kind of real time, from what I've been told. So this is going on in all of us. They're kind of this chugging along rate, and then spewing out little bits of some forms of RNA before the next steps. And so this is one of the many systems we might want to understand the rates of. But in this case, what we're going to do is take a way larger simplification. So rather than one gene slightly upregulating another gene or downregulating it, we're going to make a huge assumption, which is genes either upregulate or downregulate in a kind of Boolean fashion. Now, some of my colleagues have presented this in the early days, and the general response from some of the biologists was like, you're wasting your time, it's not worth even doing this, these are way too large assumptions. The nice thing was, we weren't just doing this as a modeling exercise, we were working with an experimental lab, and we had data demonstrating that it does work and it is useful, which is quite satisfying. But what I'll do is talk a little bit through the details of that. So the black lines with the arrows, they're saying more of this stuff. The red tags, the bar at the end, are less of this stuff. Now, if you go to a mouse, and we have the data more than that in humans, and you take the equivalent of the 20,000, 25,000, you get a big ball of mess. It's not something you can really reason about effectively. You can do association studies, like if this gene is active, other genes are active, but try and understand in a more mechanistic, deterministic fashion of like, these are the essential parts, or were they just turned on through some kind of vestigial programming, or is that a weak effect and it's only peripheral to the system you care about? It's very hard to make a determination. But we're going to have a go. And so, again, simplifying back to a very simple version. So rather than the real genes, we're just labeling them A's and B's and C's. And the dotted lines are saying like there might be an interaction here. And we can also put this in a textual form. So again, what we've got here are upregulations, we've got inhibition, so downregulations are less of the stuff. And what we then need to do, remember that process of like I was spelling out the SMT solver of the different, the wolf or the farmer being on a different side of the river. We need to spell that out as well to the solver here. So what we're going to do is talk about, like this can either be on one or other state. So this dotted line is it might be this, and we flow that all the way through down into a very dense encoding. So earlier I talked about Booleans, but if every state in your system is a Boolean and you have 2 to the very large number, you need to pack this in as densely as possible. So if you read, the way to read this is the A state is the left, most left, and then B, and then C. And this is a kind of transition diagram. Don't want to, you don't need to follow it in like super detail. I just want to communicate the idea that we can densely pack it in. We can use these heuristics for searching over the space, and we can then make judgments about that. So this is the version with this possible interaction. This is the version without. And this is an encoding that we can then ask the solver to answer questions for us about it. And so I took this full network before, like a full complex behavior. The thing that we care about in the work we did was this idea of pluripotency, or how the stem cells make choices about the world. And so some really competent, like hardworking experimentalists have gone through and knocked out like individual genes and then seen if, like, does this still happen or not? And they've done pairs, and they've moved like through like the large number of genetic interactions. And this is like incredibly difficult work. But what they found is there's a lot of things that might affect something else. And they don't know, it's like, is the OCT2 and the KLF4 interacting directly, or is it going via another gene somewhere else? And so when you wanted to make judgments about like, how could you influence this process, then you've not got enough control or understanding. And so what we built several years ago is a tool to do the same process of encoding this network of the things that might happen. We've worked with experimentalists to go through like time steps to say like which genes are active or not active at certain time steps. And we can then work through all the combinatorics of what might be happening and find the only matches that fit. So similar rules about saying you can't leave these things together. You can say these two genes at that time point are not on at the same time. So if your solution to the genetic interaction network implies that that's the case, you've reached a contradiction. And so that whole part of the search tree should be dropped off. So, tool is up here. And again, I keep jumping you from large-scale interesting problems back to very boring, simple things. But I'm trying to give you a little bit of a grasp on what's happening. So we have this smaller network with just A, B, C, and D, and I've been quite indeterminate about spelling out like what bits might be there. We've also fed in some fake data into the system to say the kind of observations about what's happening, about things being all active at the start and the second value and the final value. So like stepping through in time. We can then run the analysis. I'm still connected. And we can then get results from it. We have a lot of visualizations, and it requires a little bit of time to get used to them. But this is probably the most accessible one. So what this is saying is that I found one possible solution to this small network and that set of experiments. There are actually several experiments, and if I just kind of drop between them, you can see sometimes it puts connections in, sometimes it doesn't put the connections. What this is generally implying is that we need more experiments. And one of the things that we've been able to do with our experimental colleagues is rather than them having to do a lot of hard work searching for a lot of the space, we can suggest like, this is a really good experiment to do. This will give us good information that will help us constrain the experiment. And so the larger network of pluripotency, which is shown there, Now, I won't try and run it. One of the interesting things is, even when we take this large network and say we're going to care about one piece of functionality, and we make a massive assumption of constraining it to a Boolean network, and we use the cutting edge satisfiability solvers that have won a whole bunch of awards, it still takes about 20 minutes to run this. And the other side of this is a bit like in other spaces. It's easy to validate the results that we got to after the fact. But while I said we don't need to do searching, we do need to sometimes try different permutations. It's still an iterative process. This isn't a case where we turn massive amounts of AI and we no longer need intelligence. It just runs everything for us. So there's a lot of insight on the model as I work as well. So even under those conditions, it still takes about 20 minutes. But when I prepared earlier, manages to reduce the network substantially to more essential genes of what's happening. And so this was this is many years ago now, about 6 years ago, this original result, the science paper, and it's led to a lot of different approaches for how to interact with systems like this. And so there's kind of follow-on work with this, which I'll get to in a second. But being able to make these statements about like what we predict will happen and then validate it in the lab on a really complex space that has kind of direct impact on human health is like really very satisfying. And just a little jump here. So we've done a lot of modeling work. We've worked with experimental labs. There were also, in parallel, there were labs in the medical space who are achieving amazing things with stem cells. I don't want to draw a link between this. We're not working with any of these labs. One of the challenges is with treatments for these various conditions, there's also a lot of unfortunate side effects. So some people who are literally blind and they have to have stem cell transplants and then be able to see, but there's also like higher incidence of things like cancers in their body. And so we think a lot of this comes down to like not understanding enough about what we're doing to these cells. So if we extract them from a donor or we induce pluripotency, so if we apply these set of chemical factors to pull back adult stem cells back to like, naive stem cells, and there's a lot of reasons why that's really good, because rather than having a donor cell, which then grows into your body and is equivalent to a transplant, if we can do this with people's own cells, then we'll be able to help avoid these kind of rejection issues. The downside to this is that a stem cell, in lots of ways, is a little bit like cancer. So they grow self-renewal process, they can grow uncontrollably. So in some ways, we're interacting with complex cellular machinery. We don't understand it enough yet, but we are able to make a lot of this progress in a lot of areas. So that's kind of amazing. And what we're trying to do is contribute to the scientific modeling to advance the kind of wet lab science balance as well. And so we've done a few kind of follow-on pieces of work of more generalizing, like how does biology make a decision? So I talked through this pluripotency and also ideally like reverse differentiation. But can we generalize this to other areas of biology as well? So can we take these approaches of reasoning over complex states and teach biology how to do things that are slightly different? Okay. So yeah, this is kind of a summary. I talked about a couple of these areas. One very much in existing biology that we try and understand with computer techniques. One where we take apart biology and repurpose it into in a sense, a computer. These are some of the many colleagues of mine who've worked on these systems and produced a lot of scientific research which are trivialized into these kind of hello world programs. And that's basically done. Does anybody have any questions about that? Yeah, there's a question.
Somehow combine the hybrid between the search tree approach and the satisfiability test all combinations approach. Is there any hybrid between? Some of this information, like you make hypotheses about how these things are laid out, like in the causal dependency space, rather than just testing randomly like all the possible. I think making it more efficient.
I think there are people who do that sort of thing. One of the complications with satisfiability solvers is they often behave in surprising ways. So they've got a lot of heuristics built into them. And sometimes giving them more information makes them go faster, sometimes giving them less information makes them go faster as well. So if you're talking about a kind of approach like pre-pruning the space.
It's more like they're also testing a lot of irrelevant things.
Yeah.
So like you could use a search tree as kind of more like deciding on a space of things that matter rather than just testing all of them.
And so I don't think we have, that totally makes sense what you're saying there. Yeah, question back.
Do you have any connection with the industry in real world terms? Like you mentioned that you have a lab, right? And then you do some research there, but is there any industrial partner with you who?
Yes, I was going to give a very brief addition at the end after I covered that section. So, okay, this is a lot to explain, but if I try and give you a very loose version of this. So Novartis Pharmaceuticals have built a therapy which comes under the banner of CAR-T. So this is an approach of, and if you look at the kind of top right, what they do is people who have people who have leukemia, they've gone through a couple of rounds of chemo, they've not responded to it effectively. The technique here is to take out their white blood cells, so again, a difficult involved process. Use an altered lentivirus, so human immunodeficiency virus. Make it safe. Use that to tweak the person's immune system, white blood cells that have been removed. Make it highly sensitized to the cancer in this case. Process it carefully, remove some other parts, and then place that back into people. They've been able to take people essentially on a terminal diagnosis to something like 18% living 1 year later. So this is kind of amazing. It's amazing that it works, and amazing that you can take and alter and affect human immune systems in this way. What we're doing is helping them with modeling, like understanding why sometimes it works. And if you think back to a little bit of the programming logic at the start, or some of the things I talked about, if we could tweak this process, if we could make it so that it was, in some cases, oddly enough, less powerful, because one of the biggest problems is somebody has an advanced stage cancer, and you've just taught an immune system, their immune system, which is self-reproducing, that cancer is terrible, and their body has a lot of it, you can have a massive septic response. So oddly enough, if we could put a little bit of control engineering, if we could adjust that process, or we could find ways to help moderate that process, we would be able to help them save more people. So this is a relatively early stage industrial collaboration. We've had long-standing collaborations with academic partners, but we've just kind of started moving into this space of like, can we take these methods, can we take these approaches to understanding what biology does? Can we more efficiently run experiments, ideally outside of people, and gain more information? And then can we help understand their treatments better? And so this is there's a new banner project called Station B, which I'm one part of. And there's a link there you can go to. Does that cover?
Yes, thank you.
Great. Were there any more questions? Yeah, there was one there.
For the inputs into your programmable DNA computers, can you talk briefly about what sort of inputs into RNA proteins that you had that could trigger those initial molecules?
Yeah, I mean, as long as you can chain it up. Oddly enough, one of your biggest problems is, let's say you wanted to do some of these things, like the questions about like having real-world impact. While you could take those molecules out of the situation and you can put them into a test tube, and it would be, I have a horrible habit of trivializing some of my experimental colleagues' very hard work, but it's relatively simple to then connect those molecules to some of this logic. The really difficult thing is, if you wanted to take that logic and put it into somebody, a system which is, even if it's not trying to destroy it because it thinks it's dangerous, it just has garbage collection for cleaning up mess. So there's a lot of these questions of, can you implement the chemistry using molecules that are similar to DNA? And people talk about it as XNA, so quite similar molecules, but that your body won't recognize. But then you've got a whole series of questions of like, if you're putting this foreign matter into people, what weird effects it might have, like, and there's very individual responses to this. So you can tie in a lot of it, and more on the synthetic biology route, which I haven't talked about here. Some of our collaborators at the pathology lab in Cambridge have built a biological pathway for arsenic detection. So they've been able to deploy it in, I think, there's a few countries around the world, maybe Bangladesh, who have a skin film problem with groundwater poisoning. And the conventional approach is a chemistry approach. And one of the snags is it requires careful handling, because the main thing you do is produce arsenic gas, which is even worse if it's immediately in front of you. So this route the pathology lab are taking, they're able to take a sealed biological package, so there's no environmental exposure. They can take water directly from a well and pour it through. And they've done a lot of work on like understanding and usability. So like, how do you communicate this like levels? Because if you've got a choice between like different wells, maybe there's some arsenic in different ones, and if it's very low levels, maybe that's tolerable. If it's high levels, you have to convince people they need to go a lot further, or that well needs to be closed. So that's a really impressive humanitarian project. But again, we're not directly involved in that. But
I guess I was wondering from an applications approach, from the examples that you gave, you had to engineer these short regions, and they were important. How would it work with, for example, I'm expressing a certain protein, or for example, I might have some cell-free RNA that might be a signal to the biomarker for a tumor?
Yeah.
How would it work in that case?
So in that case, you'd probably take more of a synthetic biology approach. Are you talking about doing this in an industrial setting or human health?
Even in a test tube. So if I just stuck some RNA in, and I wanted to detect that, do an OR on that, is it possible to do that?
Generally, yeah. There's kind of co-design. Some things are easy to do. We have this as a challenge that while it seems easy, if you want to make some arbitrary structure, arbitrary length, especially as they get longer, the DNA synthesis companies are less able to do that. There's some impressive new ones who do direct synthesis, who lift some of those restrictions. But you've kind of got constraints on both sides, the biosensor side and what you can then see and respond to. But it's possible, but it's hard. More questions?
All right, thanks very much, Colin.
Okay.
Thanks again, and looks like we have pizza, and we definitely have drinks. So thanks again to G Research. Please do check out their careers page if you're interested, and have a fantastic Christmas, everyone, if you're not persuaded. And hopefully see you all next year.